Hello everyone, my name is Tan Ka Hui. My metric number is 229377. So I want to present the fluid properties and their engineering application. What is the objective of my presentation is let you all understand the fluid features and understand the application of fluid properties in engineering field. So what is fluid? Fluid defined as a substance that deforms continuously under the action of shear stress no matter how small. Fluids are categorized by their ability to flow and do not resist shear force in the same way solids do. Fluids can be either gas and liquid. There are There are some fluid properties which is density, viscosity, specific weight, vapor pressure, temperature, surface tension, compressibility. Fluid properties are key characteristics that define the behavior of a fluid under various conditions. These properties are important for understand how fluid move, interact with surface and responds to forces. The density of fluids is its mass per volume. The unit of density is kg per meter cube. Density can affect buoyancy and pressure calculation. Liquids are essentially incompressible, whereas density is highly variable in gases nearly proportional to pressure. For example, water at 4 degrees Celsius, its density is 1000 kg per meter cube. Next is dynamic viscosity. The unit of dynamic viscosity is Pascal time second. Dynamic viscosity is measure of a fluid resistant to flow. When the high viscosity of the fluid, it means it is a thicker fluid. So the dynamic viscosity will impact the flow type of the fluid, whether it's laminar or turbulent. So it will impact buoyancy and hydrostatic. For example, the dynamic viscosity of water at 20 degrees Celsius, the dynamic viscosity equal and approximate to 1.002 times 10 power of negative 3 Pascal times second. The unit of vapor pressure is Pascal. Pressure at which a fluid vapor is in equilibrium with its liquid at a given temperature. It indicates the volatility of a fluid. When the fluid have higher vapor pressure, it becomes more easily evaporated. So for example, water at 20 degrees Celsius, the vapor pressure is 2.34 kilopascal. So, fluid flow in pipeline. For example, in oil and gas pipeline, denser crude oil require higher pumping power and stronger pipe. The key equation is the Bernoulli's equation. Incorrect assumption about density will lead to underperforming of the pump. Distillation process. In distillation process, difference in vapor and liquid density will affect the phase disengagement in the column and tray design. Liquid-liquid separator will use density difference to separate the immiscible liquids. Application of dynamic viscosity in engineering field. High viscosity fluid require more energy to pump. It needs stronger pump and larger pipe diameter for viscous fluid like syrup, oils, or polymer solution. Lubrication and hydraulic system. Viscosity is essentially for creating a lubrication film between moving parts. In systems like compressor, turbine, or engine, the low viscosity is classified as a poor lubrication, leading to wear. When a high viscosity fluid it requires excessive energy loss, it will lead to excessive energy loss and heat generation. In boiling and distillation, the fundamental principle. A liquid boil when its vapor pressure equals to ambient pressure. It is the fundamental principle of boiling. So, in distillation, components are separated based on difference in vapor pressure, which is volatility. More volatile compounds, it means the higher vapor pressure compound will vaporize at lower temperature. Storage and safety of volatile chemical. When it is a high vapor pressure substance such as propane, gasoline, it will generate high internal pressure in storage tank. It will affect tank This affect tank material selection, vent system design, explosion and flammability risks. For example, LPG storage tanks must be designed to withstand high vapor pressure at ambient temperature. So now we look to the heat transfer efficiency versus pressure drop in heat exchanger. Economic evolution will be used to compare the cost of energy and also process gains. What is the symptoms? Exceeding the pump rated pressure heat, lower flow rate than required, higher energy consumption, potential safety concern with pump cavitation or mechanical stress. So, what is the strategy to overcome the problem? First is optimize heat transfer surface versus flow resistance. Use enhanced surface tube instead of increasing the number of tube. Choose a moderate number of ballasts to balance heat transfer and flow resistance. Besides that, add a second heat exchanger in series or parallel also is an ideal way. When you insert in series, it will increase the heat transfer without needing high turbulence in one unit. When you insert in parallel, it will split flow, reducing individual unit and pressure drop. Thank you.